Yeah, I try to give an overview. I'm not sure if I managed to make it brief, but so I may have to talk a bit faster. And this title here, From Moving Bits to Moving Minds, that is meant to span our considerations that range from very low-level aspects to really the human perception and the way in which we can modify human perception in order to make multimedia systems work. And as I was nicely introduced by Christian, I don't have to say so much about myself. Currently, SINLab and myself, we are involved in 3 projects. There is the Mirage project, which is a rather small, short cascade fund where we can use remote interaction. We have the Imagine project that's just finishing, which is a bigger EU project on use of 5G for new ideas. We have Mishmash, the brand new AI center with arts that I'm going to talk about at the very end if time permits. And we have Drive, national project just came, which is all, we just got the money and we start hiring people who are going to also work on remote presence. And classically, in the last couple of years, I haven't worked so much on streaming infrastructures anymore, but just assumed that those exist and others take care of that, like people here, and that I can just adopt that into our systems. And we've gone more to remote interaction, to the performance in both interpretations of the word, to support VFX and also immersiveness, including immersiveness for games. When to come to us, and I hope you do visit us, you find our new building, which is now well, maybe getting towards 20 years old, and you find us on the 5th floor, just up there, and hidden away in tiny offices where your space, that is, we are so envious of the space that you have, you can't imagine it. We are part of a larger group, the Networks and Distributed Systems group, and these are the people that are currently official members. And they work on lots of different topics, but SINLab is only a small subgroup of this. The people who are a combination of immersive technologies and 5G. And you see we are not so many and include not only computer scientists, but also music technologists and neuroscientists. So we are so broad in order to be able to understand how we can do this immersive interaction. We have some friends who are closer to us philosophically. Those are the ones that agree with us that we should search for bottlenecks in systems and not have a hammer and look for nails and do the same thing over and over again to get more papers out, but that we should start with either an application, which is more my approach, or with general knowledge of the internet, like for example, there is buffer bloat, and start from there and go to solve this problem that we have. And then we come up with work that needs to be done in places all over the place. It could be just new ways of developing an operating system. Like, are you able to virtualize more efficiently if you're not using a classical operating system, but if you're using a unikernel that is just linked towards a classical application, doesn't need your user kernel switches all the time, but it's just super restricted, easy to boot, and still delivers the full functionality of an operating system. It can be something that is in the network stack, like, for example, developing new approaches to congestion control, like time-based TCP, which gives you a cleaner implementation and a cleaner view on how TCP should behave based on the feedback signals that you're getting. And because we also look at 5G, it's very interesting to use machine learning methods in order to look at applications and see how you can manage both the communication and the computation resources in a large-scale 5G networks as a single thing. And that is something that is not completely absurd, even though telcos like the Norwegian Telenor, our eternal friends, don't like to think about because it complicates their life and the life of their management people. But in Spain, for example, Telefonica, they are doing that, right? They're offering mobile edge computing as a service, and they integrate the placement of that together with communication performance. And we also have applications, and we want to know how users perceive applications that are working on top of these infrastructures after we've fiddled with them a little bit. And that means that many times We make tiny changes somewhere under the hood. We don't go to the place where you make beautiful abstractions that millions of people can use, but we just show that something is possible and how it affects people. And since immersive applications is our topic right now, we need a couple of toys. And the toys that we have is, of course, a 5G indoor testbed, which is tremendously unstable and just a pain, but we get money to use it. We have our lovely robot arm and robot hand, which we are using as a remote entity in order to be remotely physically present in a different environment. We have Rococo Smart Suit, which gives us a very efficient way of tracking body motion. Of course, Vive trackers. We have a haptic feedback in-air device, haptic feedback vest, and of course the usual things in order to deliver augmented reality and virtual reality information. And when we do research, we try to build systems and then explore them on people, and preferably together with our project partners, so that we are not alone with our tiny little team of 5-6 people. And that comes to so we can come to the first applications that we've been working on. So these are two examples for which we have mainly worked on live tracking, live understanding of where a user or a camera is in the real world, so that we can mix the real world and the virtual world. In the third live project, an artist, incidentally from Vienna, created a virtual world in Minecraft, and then he was present in the first person, walking around as his avatar in this 4x4 space with an Oculus headset, and we were responsible for tracking his body pose, whereas our friends from South Africa, they were responsible for tracking where his head was relative to the body. So this little Minecraft avatar could run around and could really look around while he was followed by some pigs in this case, and sometimes by some zombies. The same technology, this tracking, was also used in an EU project called Ladio, where it was used in order to always figure out where the camera is in order to integrate within 5 minutes after a shot virtual elements into a real film scene and allow the cameraman and the director to figure out if it has to be reshot. So you can't make a real movie and have the actors run around with augmented reality headsets, right? Doesn't work. But at least the director and the cameraman should know that this person is staring at the feet of the dinosaur instead of the mouth, right? And you can see that after a couple of minutes. And incidentally, it didn't have to be 5 minutes. It was actually working in real time at the end, which was quite nice. That, of course, means that we had to do some work, because I was stupid and said, of course it is easy to do SIFT, feature extraction, in real time these days on a GPU. And then I worked on that for 3 years, until it did. And the thing that we used was SIFT, scalable in variant feature transform, which is still the state-of-the-art non-machine learning feature extractor for tracking points in 3D. It's still typically the best, with 2 or 3 modifications over the years. And whenever it comes to competition between feature trackers that are AI-based and SIFT in a general data set, SIFT still wins. So it's nice to have been able to build one that actually runs in real time. And what does it actually do? It takes a grayscale picture for every frame that you have in an incoming video, figures out which of the points are interesting, and then defines a position, an orientation, and a scale of this point for that can be matched to a point in a different picture of the same scene. And in that way, you can actually have a couple of cameras, or you take a camera that moves, figure out where every point is in these different scenes, find exactly the same point and its orientation in a different frame, and use that either for figuring out where the cameras are relative to each other, or in order to figure out where the point is in the 3D space. The number of steps for that are slightly annoying. You take an image, you have to upscale it so that it is twice as wide and twice as high. Then you have to emulate every possible size that this image might have. So that means you need to downscale it to every possible resolution. That, of course, is a bit overhead. So this is emulated by a mathematical approach of blurring this picture incrementally without downscaling it until the blur is so strong that it's equivalent to a downscaled version. So I take this perfectly upscaled image, blur it 7 or 8 times. Then I take the third last of those. Why it's the third last, you'll see in the next slide. And downscale it back to the original size. Again, I make 7 or 8 blurred versions, take the third last, downscale it, and so on, until I get down to a tiny image of 128 pixels wideness, or until I hit a configuration parameter. Then I take the images and compute the difference between every pair of images in the same resolution. So I get the difference of Gaussian, which is essentially how intense is the change of these pictures when I blur them once. And I do that incrementally. So out of these 7 upscaled images, or 7 images that have been blurred, I get 6 difference of Gaussian images. And then I need 3 of these every time in order to find out which pixel is an extremum compared to its 8 neighboring pixels, the 9 pixels that are more blurred and the 9 pixels that are less blurred. And when I find such a pixel, and I do find such pixels, obviously always, they are a remarkable extremum. They are a feature point, something that is easy to find again in a different picture. So when I have this, I only make a little check to check is it a strong enough peak? If it's a strong enough peak, then I know I will be able to find this thing again in a different picture. And then I just need to look around in my neighborhood and figure out if maybe I'm doing a Gaussian curve on top of it and see where the peak is in the Gaussian curve, but in 3D. And maybe I change the pixel in floating point areas a little bit around it to find the peak that is actually the strongest peak, not in integer coordinates, but in floating point coordinates. And that's the pixel I'm going to offer for the next stage. Then I figure out in which direction do I have the strongest change of brightness. And I do collect these changes of brightness for every pixel inside the region, where the size of the region depends on where I found it in this pyramid. So if I found it very late in the pyramid, I take pixels from a long radius into consideration, and if I find it at the tip, then I just take a few pixels into consideration and check how much did my gradient, the intensity change, and put that into a bin of 360 degrees so that I can see in which direction do I have the strongest change in brightness. I make a histogram to find out in which direction I have the largest one. And if I have found one, then I check if I find up to 3 more so that I have up to 4 possible orientations in which directions in which I have a pretty strong change of brightness. So I get an orientation for in which direction does my pixel's neighborhood change most. And then I take a neighborhood. Again, the size is defined by how deep in the pyramid I find it. And I create 8 histograms with their brightness change put into a histogram of just 8 bins, which are computed as floats. And I end up getting in total 128 floats that describe exactly the neighborhood of this pixel in brightness change for the whole environment. And that has been proven to be incredibly resilient to rotation and scale, obviously, right? But also to rotation in depth up to 30 degrees, which is actually quite exciting. Now, shift from 2004. our code in CUDA was from 2016. Why do I still talk about it? It's because people still complain about why is it not portable to other CPUs and to other GPUs. So we have just recently finished a port to something called Cycle. Cycle is something that Intel has proposed in order to not being the only one who produces GPUs that nobody uses for computation. So instead of inventing a new thing like CUDA, a completely new dialect of C++, they have made Cycle, which is nothing else than a C++ template library that works perfectly like a template library, but if the compiler understands it, it can auto-parallelize to Intel GPUs, AMD GPUs, CUDA GPUs, to FPGAs, to whole clusters of machines. So the big question is, can it compete? That, of course, needed some porting and some testing. So Muhammad, who did the ports, made some checks on a variety of images and a variety of considerations, and went through the stages of SIFT and figured out that, well, in general, CUDA is faster. That makes a lot of sense. The most important element is that this Cycle is incapable, these days incapable, of supporting interpolation hardware that GPUs have. So it's not able to take a floating point coordinate in a pixel space and give you the average value across 2 dimensions. And as long as we are in a stage of an algorithm that is very good at that, CUDA wins. So CUDA uses nearly no computation power compared to Cycle. But when the algorithm is very easy, when you just go linearly through memory, then Cycle wins because the Cycle compiler is just a better programmer than I am. So, bad luck. And this is the kind of thing that we do a lot. Go down and try little algorithms and see how things get faster. But sometimes we can't get it fast enough. We need more computers. And for that, we have, for example, come up with something that is called device landing. Anybody who has heard about that? Right. Device landing is the idea, and Smart I/O is a product. And what you do is essentially you take computers that are interconnected by PCI Express instead of Gigabit Ethernet or something. And this PCI Express is then just an extension of your bus. So your computer can actually address or access all memory addresses in all the other computers on the same fabric. You don't have to go through layers and layers of network stacks in order to get down to the physical layer and send stuff. You map things up, it appears as addresses in your computer, and you just write to that memory, and it appears in the memory of the other computer. So while most of these cluster computations where you try to make cluster computation and use devices of other computers need to have abstractions that go up to Ethernet or maybe even to TCP level, we can just say, oh, I want to see a segment of a memory and another segment of the memory, and I want to see a segment of the GPU's memory in that other machine, and you map it into the address space of the computer that wants to read from there or wants to write to it. And that's nice. But the fun stuff is that when you insert a card into your computer these days, an NVMe disk, a network card, a GPU, everything that you do to interact with them these days is actually memory mapped. Its command queue is a memory address. Its memory is a memory. The interrupts that it sends to are in the memory of the CPU that controls it. So essentially, we can map everything over the network. That is unexpected. And we get to this situation where we can say, well, this computer, it has a GPU. That computer wants a GPU. Well, let us map the registers and the memory of this GPU over a PCI Express link to the other computer. And as soon as it's fully mapped, we raise a hot plug event on this computer. The driver of the device is loading, and it can interact with this device as if we just plugged the card in. And it sounds cool, right? That was the original idea. It's just that it gets slightly more difficult when you actually try to do it. First of all, you have to figure out where the registers are that control the device. You map that to the other computer. And that is, of course, not a bigger problem, except that you need to, and you get the addresses that are mapped. And because this address is not the same memory address for that computer as the address here, the PCI Express non-transparent bridge gets the task of mapping the addresses in writing. If the device is meant to write something back to the other computer, you need to register a buffer on the computer that is the one who is borrowing the device from the computer that has the card and that's lending it out. So that needs to be registered on the other computer so that this device is actually able to see it. And then finally, we also need to be able to tell the CPU on this side when you have completed a job, when the GPU has completed a job. And for that, we need to take the interrupts and map the interrupt vectors that are in this CPU that is landing it, so that this device can then raise an interrupt in the memory address that is mapped from the original interrupt in that CPU and tell it that it's ready with rendering an image, with finalizing a computation, or with whatever instruction you have given it. And that works nicely also for sharing disks across the machines, for sharing GPUs, for sharing RAM anyway, for sharing network cards. And you don't even lose any kind of performance compared to the bandwidth of the PCI bus that is inside your computer, because obviously the bridge translates addresses in line speed as quick as PCI Express can send data. And the speed of the interconnect is the same as the speed inside your computer, because that's what the PCI Express standard says. So after having mapped the instruction registers for this device in the one direction, the buffers that you want to communicate with in the other direction, and the interrupts to report a job that is well done in the other direction, we are finished. And when you compare the throughput of a transfer between a computer that contains the GPU and a computer that lends the GPU from another machine, you just don't see the difference. It does have some latency, like 20 nanoseconds extra latency, but that's definitely better than walking through a complete network stack in order to communicate. The little challenge of PCI Express is, of course, that it can nowadays only address 128 devices, and that means not 128 other computers. It means devices entirely, right? RAM, banks, GPUs, CPUs, whatever. Everything gets a number. So we are waiting for CXL to give us more space, more address space, and then maybe work on this later. And right now, our friends at Dolphin, who have made this into products, they are working on how you can do it with virtual machines, and that is working. The next step is how can you use that in order to have a high availability solution where the virtual machine that uses a GPU and a disk in another machine can crash. You transfer and keep this volume alive, and you do not need a copy of the GPU or the disk. You can just remap it so that you can continue working on exactly the same GPU, the same disk in the same state without transferring anything or restarting anything. You just stop the computer that is the destination, transfer the state, reconnect to the devices, and you're up and running again. Which is not as crazy as you would think, because when you plug something into a Mac, for example, and it uses a lot of address space, then the Mac has this tendency to freeze for a few seconds, remap everything, and then come back up with a completely new mapping of memories to devices. And if the Mac can do it, why not do it generally for all Windowses and Linuxes out there? All right, so now we can go up a little bit from the things that happen at the lowest possible levels that we are working on, and look at the nice application that is now actually getting a bit immersive. We had this tracking scenario where this artist from Vienna had built a Minecraft world and was working around in this in first person. And we needed to make a big space for him that was a 4x4 meter carpet so that he could navigate with his own physical motion in this virtual world. And whenever he was crossing the threshold of the 4x4 meter space, then he had another meter as a scrolling area so that his avatar would run in the direction where his body was pointing. And we came to this idea that, well, there is this thing called redirected walking. It uses the effect that we humans, when we are not exploring, when we're not experiencing any input from the real world, we will eventually go in circles. And you can see how easily this happens when you see this video of one of our master students who worked on this topic. He's trying to go really straight. It's not very far, and he's already going away from the straight line. So it means that we are not consciously aware of how of small deviations of rotation between our internal understanding of a coordinate system of the world and the real world coordinate system, right? Even our brain is not perfect. Why can't we trick people and make them go straight in a virtual world while they unconsciously go in a circle in the real world? Well, we can, right? That has been shown. The question is, how intensely can we do this? How small can the space be before the people are no longer happily accepting subconsciously and think that this is straight? And that is an idea that works for games, that works for exploration, but it's also something that when you imagine people working in a VR, if they stay in VR for the entire day in order to do their job, which people don't do today, right? Because it's unbearable. Then this kind of thing where you are immersed fully with your entire body is stretching this time until you have to give up and leave the virtual world. Actually, Otto, who was the artist from Vienna, he stayed in Minecraft for 6 hours in a row and felt super. I think that's a bit crazy, but hey, these guys are crazy, right? They're artists. So we wanted to know what can we do when we redirect. We looked only at 3 different approaches to redirection. This one is the easy one. I don't talk about it very much. Translation gain just means that you are sped up and slowed down into one direction. And you can use it generally in order to translate every movement you do in your real world to, for example, twice as much distance in the virtual world, or you can do it in such a way that a movement in one direction is scaled up by 10% and the motion in the opposite direction is reduced by 10%, and then you are going to drift while you're moving back and forth. We don't talk so much about that. Rotation gain is the effect that when I look around, I can, every time when I look around, when I turn my head, I'm going to lose a bit of understanding of my rotation and my orientation in the real world. So I can over-twist and rotate not by 100% of my real world's head's rotation speed, but I rotate by 120 or 80%. Right? So I rotate my virtual world coordinate system around the position of my avatar by 5, 10, 20%. And so when I turn back, I don't do it in the same speed. So that after having looked to the right and looked back, the rotation between my virtual and real world is maybe 20%. And then I have curvature gain, and curvature gain is what you have seen in the short video. Curvature gain is you go into one direction, and we're twisting you a bit while you're going. Under-twisting and over-twisting depending on where you are in the real world, so that you preferably don't run into walls. And then we developed that for a while. Took a year or something. and made a user study to look at how strongly users perceive the redirection and what's the experiences when they do that. For that, the students created a couple of virtual environments. There was a recap house where you could just walk around freely. There was fire drill where you had to go in zigzag routes and push some buttons. The track and field where you were essentially doing a 100-meter track and you were rotated. The witch's cauldron where you had lots of different shelves. You had to walk to a shelf, pick something up, go to the middle of the room, put it into the cauldron. And the dungeon where you walked around and opened chests to find gold. And, well, we used our various rotation and curvature gains to check what's going on. And for track and field, for example, we applied curvature gain. So people think in virtual world that they go straight, but we rotate continuously the relation between the real and virtual world. And you can see that for a radius of a circle that is infinite, that means we have no mapping, the lines stay straight, people are pretty happy. Not perfectly happy, because they know that they are redirected even if they aren't. But up to a radius, circle radius of 7.5 meters, we are actually keeping our candidates hardly able to notice it and very happy with the effect of redirection. So at a radius of 7.5 meters or 50 meters diameter of a circle, they feel that they're still going straight. That is not exactly the space that you have in your living room, so having perfect redirected walking in your living room is probably not going to work out very well. But you can have that in, for example, a sports hall in an open area. In our case, we did it between our two largest auditoria. There was enough space in order to let people feel this. And the other restriction we had is that people are not allowed to actually run the 100 meters, because if they run, this changes and they end up in walls. So we don't want that. There were actually some examples of people who were not used to VR and they were so enthusiastic that they actually started running, and then it was like, oh, stop. Please don't. But we didn't hurt anybody. The ethical constraints were obeyed. Rotation gain is also pretty nice. And we were able to easily allow a rotation gain of the head by up to 10 to 25%. But the interesting thing is that you could make it more flexible by having so-called distractors. The distractor is, if I don't wait until the scene, my scenario, my dungeon and the activity in there is leading me to rotate my head, to turn my head, and I don't rely on the users just wanting to look around for looking around's sake, we can force them to subconsciously want to turn the head by introducing things like, in our case, we had this will-o'-the-wisp, such an Irish fantasy thing that is glowing in the dark and making a little buzzing sound. And when they buzz around your left side of your head, then you need to turn your head to the left, right? You can't avoid it. The second thing was a sorcerer who was throwing fireballs at us. And then, of course, you also have to turn around and react to that. If you do that, we were actually able to rotate 40% more before people noticed that there was any redirection. So from having a rotation that is acceptable of 10 degrees, we could easily go to 14 degrees. However, we can't push it as far. So it's cool that when you do not introduce distractors, people are earlier aware of the fact that they are rotated, but they are happy for longer. If you use the distractors and you are exceeding the limits, then people's quality experience will drop rapidly, while they actually keep up with it for a longer time. And that was a cool thing, and we are trying to explore it more. And in addition, we have started some exploration on how much audio scenarios, the audio environment matters, and now how much the quality of the scene, the naturalness of the scene affects the ability of that we can use for redirecting people. All right. But presence in the virtual world is old-fashioned, right? We want to be present in the real world. And for that we have boards, a humanoid robot that could be our avatar in a remote space. Now there's a little challenge. That hand costs 100,000 euros and the arm 50,000. So we don't have a second arm, we don't have a second hand. And it's not very remote in this scene because we just want to see how much control you have and how accurate you can translate your own body motion into the motion on the remote side. And you saw Özgür, who was taking one test. She was lifting these little cubes out of a box and moving it to the other side of behind a little wall. This is called the box block test, and it's a standard test for people who have had strokes. In order to see how well their body control is, they have to take this test again and again. And we adopted that to figure out how much control you have if it's not your own body, but a remote body. And it's one of two tests. The other one is the so-called Jepsen-Taylor test. And in order to do it remote, we have this little stereo cam that is for now standing on tripod. But as soon as somebody lends us another robot arm, we have also some code that it can track the head. So you have an Oculus headset. The Oculus headset's motion is translated into the stereo camera's motion, and you can actually look what you're doing from your own perspective. We have only one arm, so right now we can only do one of the two things. Why does it do that? It shouldn't. Okay, these are the two tests. This one is the box and block test. And this is the Jepsen-Taylor test number 6, which is essentially just grab a can and put it onto this shelf, on the little shelf. Very simple things for people who have problems controlling their motion, which we have in the remote scenario. And then we made it harder by inserting artificial delay, network latency of up to 200 milliseconds. We ran user studies for 4 weeks in a row, so quite a few people who had to do these tests. And then we tried to figure out how much latency matters and how intensely it affects the user's performance. And you see that the average number of blocks that people were able to move in a minute, I believe, was 5 if we did not induce latency, and it was dropping to around 3 when we introduced up to 200 milliseconds of delay, and you see how it goes down quite easily. And the time it takes to complete this is, in order to complete the Jepsen-Taylor test for moving the boxes, is also growing quite linearly when we increase the latency. And these stars up there, they indicate how much statistical significance we find in the data, because the variance here is massive, because people are very individual. So some people managed 2 and others managed 12 blocks in the minute. So it's a very diverse performance. Some people figured out that you do it like this and it's easier to fix it. Others got stuck with their little finger and couldn't move the robot anymore. That's how it goes. And these were the objective scores. What happened with the subjective scores? The first is how strongly did they perceive the delay compared to the actual delay? And we gave them questionnaire, how strongly did you perceive the delay, on the classical 1 to 5 scale. And you see that people are, again, very diverse, and it grows quite nicely with the latency, but it doesn't become too bad. It's interesting that the box motion test has a bit stronger effect. And this one is the same, but in this case we asked about the difficulty, and again people notice that it gets more difficult when the latency grows. Why does it matter? We made tests with people in Spain, and the latency is roughly 220 milliseconds, right? Network latency is 20 milliseconds. However, the latency of the base of the robot is 250 milliseconds, right? So it's not ideal. And then we have done that over the network. As I said, we did that with Spain. We had our robot arm on our side of the communication, and there was a robot hand on the Spanish side, and it had to go over 5G, but there is no 5G connection between Spain and Norway, so we have a 5G in our lab, we have a 5G in the Spanish lab, and we have a normal géant internet, high-speed interconnect between them, and we could make it work, and it was quite nice. So you could do first-person control of our robot from Spain and get some motion out of it. So now these 250 milliseconds plus the network delay. That's of course something that we would like to predict. And hand motion is a nice graph, right? So it's not so difficult to predict where a motion is going when it first starts. So we have, in the first go, tried to define an RNN in order to predict the motion of the hand. But the important part is that if we restrict the motion to gestures, to just 4 or 5 gestures that are repeated, then the story is useless because that's what a robot will do autonomously, right? If the number of things a robot can do is 5, then you have an autonomous robot and you press a button or you talk to him and say, go. We need free motion. Otherwise, it's meaningless. So how good are we at predicting the motion, the hand motion of a human body freely? Well, so far it's could be better. The hand has 24 different joints, so it can do this, it can do this kind of stuff between the, and it can even do this, like bending the fingers inward, right? So you can grab something with your balls of your hand. All of that can be transferred, and when we do the prediction with different milliseconds of latency, then we see that the absolute error of our prediction, and that's the absolute error in terms of distance in degrees between the joints, the actual joints of the hand and the joints of the robot, is growing quite rapidly, and it starts already at roughly 20%. That is not so terribly satisfying, right? So we definitely have to work more on this, and we have a project that goes on for 3 years, so I guess it will go somewhere. One thing that is going to help is that this Mirage project has given us a hand from a Greek company, Haptikos, that has touch feedback. It also doesn't rely on IMUs. That means that it's just physically measuring how much we pulled the hand down, and you don't have to have a very clean environment with little magnetic fields in order to make it work. And then you can do essentially the same as we can do with our old Rococo hand, but now with the ability to feel some vibrations in the fingertips as soon as we touch something. Now, little problem. While we did our user study for 4 weeks, we broke our touch sensors in our hand. So now the only thing we can do is we see the motor's torque. We see how much the motor must work in order to close the gap between the fingers, and deduce from that is touching something and use that as a signal. Well, I understand that you have a colleague here who works on better sensors. I talked to him. Maybe we can find something to do together. And then we are not happy to stay there, right? So the next thing is that we would like to see if we can't predict this from the brain. It will not work very well as long as I don't have network switched on. Okay, Ederome doesn't want to come. Bad luck. Right, so I'm going to check it out later. The point is that for the last 2 weeks of our data collection, we had the students and ourselves wear an EEG cap and collected data that was trying to figure out how much you can predict when hand motion is going to happen. Now, we're not very confident that we can see this is the right hand that's going to make a gripping motion, but it can at least warn us that something in the context of the remote scene is going to move, and it's going to happen in roughly 200 milliseconds. Because we know that we're going to get a signal from the brain roughly 200 milliseconds before the hand actually moves. And if we can use those 200 milliseconds combined with some understanding of what's happening at the other side, then we can start moving the robot 200 milliseconds earlier. And that is quite good compared to the 250 latencies that we have. And actually, 3 probes on the head are sufficient in order to figure that out, which is good because there are some modern helmets that are essentially VR headsets with strips just on top of the head and around the base. Well, that's the next 3 years. So let's see where we go. We started collecting and we are starting experimenting, and so far we don't understand the data. But the expert from Texas that we work with, he tells us that it's going to be very, very, very high level, and you can't expect very detailed knowledge from that. But since you already are there at detection of all kinds of sensors, we want to do stress recognition, and there's data collection going on in Milano right now. We try to figure out what are indicators of stress based on RGB and infrared video, audio, eye movement, electrodermal activity, heart rate variation, and muscle activity, and see how this can help us to figure out if somebody is stressed in a scenario like in a control room. The student who does that is a researcher at the Institute for Energy Technology in Norway, and she tries to get a PhD with us. And these energy technology people, they are making control rooms for nuclear power plants. And the idea is to figure out if the operators are stressed so that they can help them, fix them, replace them before something goes boom. And that is a collaboration that comes together with our AI Center Mishmash, just started a 5-year activity. It's the only center for AI in Norway that is driven by the arts, by humanists that are creative people. This is Alexander Jensenius, the boss, and he has been creating a consortium that involves absolutely every humanities faculty that exists in Norway, and made that into a consortium for his application. And for some reason, since everybody was involved, got it accepted, right? And here we want to work on AI for artistic performances. Essentially, it means how can we do real-time interaction between embodied AIs and humans when they make music, or when they dance, or when they want to create a film. AI for artistic processes, classical LLVMs where you do question response. How do you use creativity with the help of AI in the health system? How do you make people engage people in jobs that they need to, in tasks they need to complete for recovering the health? How do you do it in education? What is the challenge for the law people when you have to maintain your IP of your creative work that is built on AIs and that's interactively changing? So how do you create IP of that? How do you use AI how do you create cultural heritage and maintain it when you're a librarian and you're supposed to keep all artistic output of the country recorded? How do you do that when part of that is an AI? And then our work package, the work package for creative problem solving, where we ignore all these art stuff and we want to use it in other scenarios, like, for example, how do we do that for the shipping industry, to run a harbor, how to run a ship? People are from all over the place, and we have put ourselves up quite a few questions. And ours is, how can creative AI enhance human agency, control, and expression in problem solving while adhering to physical, legal, and societal constraints during the creative process? It means that whatever we do in the whole of Mishmash, it always is about the people using AI or interacting with AI, never about AI being autonomous. Others are doing that all the time, we don't. And with that, I've talked very quickly through all the different layers. And I hope that somebody got some questions that they want to ask me, because, yeah, I want to talk to some people about cool stuff. Thank you.